Hi guys, so far we've made the inverter schematic and the icon view of the inverter. Now let's move on to making the layout of the inverter. Now to make the layout, what do you need to do? First go to cell and make a new cell. You can use the shortcut here. The shortcuts are on the right hand side. Ctrl N is the shortcut for making a new cell. So click. After you click on that, make sure that you select layout since you are making a layout. Now, while naming the cell, make sure that the name of the inverter schematic should be same as the name of the layout. So I will write INV. Both should match. And then say OK. Now you'll see one inverter layout cell has been made. Let's click on it. Yes, we are in that cell. Now let's go to components. Now in components you'll get to see that there are various components. Now these components are different than what was there for schematic and layout. I'll just tell you what are they. This is the NMOS, that is our N transistor, PMOS. Then we have the active regions, which is nothing but the contact. Then we have these metals. This is a metal 1, metal 2, metal 3. These are the pins for the metals. If you want to draw a metal line somewhere, so you just insert a pin. These are the contacts or via. Then what do we have? P well and N well. Wells are used to avoid latch up. Now what we'll do, just take a look at our schematic once again. And what do we need? We need one PMOS and one NMOS. Okay, so let's just go to layout and click on PMOS, go to the workspace and click again. Then select one NMOS, go to the workspace and click again. Now, as you can see, this is the polysilicon and this is the drain and source. Now, I won't say this is drain and this is source. I won't specify that because it is very designer specific. Now, if I rotate it another way, this might be the source and this might be the drain. So it depends on me, which is the drain and which is the source. So now what do I do? Since this is the polysilicon and the drain sources of the PMOS and NMOS, I want the inverter in vertical position. So I will click on the inverter and go to edit and rotate 90 degrees clockwise. If I had the inverter in the transistors in this position, then it would be a horizontal inverter. I want it in vertical. So I go to edit, rotate 90 degrees. Okay. Now, what you see here, the hashed lines and the dotted lines, these hatches and these dotted lines, they are the regions. We are using electric uses a twin tub method. Okay, so this is one tub and this is the another tub. Now which tub? Well, I think you should know about it. And then now what to do? We'll just align them. But since these are two different regions, make sure that you don't overlap them. Overlapping will give you an error. So they should be spaced apart. Spaced enough, but not so large that your PMOS is at a large distance from your NMOS. So we'll just keep the NMOS and PMOS at a considerable distance. Okay. Now we need to connect the drains and source to each other. Now we can't make the connections directly. We'll need a contact. So we use the active regions. P active region is used for PMOS. So I click and click here. P active, N active, click and paste. Okay, so I have my regions in place. But now, as you can see, the sizes of these are, you can read here, right? 3 cross 2. And this size is 5 cross 5. But when I designed my inverter, I made sure that my size is 10 2. My width is 10 and length is 2. So here the length will definitely be 2. This is the length. But I want to increase the width. So what do? I click on the device and then I open properties. In properties, I increase the width to 10. Similarly, I click on the device and open properties. Now you can open properties like this also. Here, properties, object properties. As you can see, Control I is the shortcut here. So I click 10. Okay. Similarly, I want to increase the size of these contacts also. It is not fair, right? The drain and the source is something like 10 in size and the contact is just 5. So we'll just change the properties of. So now here we don't have something as width and length. It is just a contact. So there is X size and Y size. Since our inverter is vertical, we will have to increase the Y size. So I make it 10. Similarly, do it for the remaining ones also. Now this inverter is ready, but you can see it is not completely ready. We've just placed our components and the space looked jammed up. So what we'll do, we'll just zoom out. So we'll go to view, we'll go to window and then say zoom out or just Control 0. Okay, now as you see, my N regions and P regions are mixing with each other. So I'll draw one box like this and pull them apart. Okay, now after we are done with this, make sure that you align your polysilicon in one line. If you want, you can turn on the grid to do the same, and then you have to align your active regions too. Now, why do we need to align them? Now we'll have to make connections from the drain and source to the active regions. Now, if the active regions is misplaced, then the connection is not proper. You get some extra connections. Now that connections we don't want. So what do? We just put them in line. Okay. Now after this is done, left click on one and then right click. You should get such a connection, a green colored connection. If you are not getting the green colored wire, then just click on it and press delete and then again make the connection, maybe from the other end. Then left click, right click, left click, right click. Now we have connected our drain and source to the contact regions. Now we'll bring it to closer. Yeah, but make sure we don't bring it too close. Now you can see something written on the top here when I move the region, right? This P active spacing is 8, 7.5, 8. Okay. Now the minimum spacing, that is the minimum DRC rules allowed by electric, is 3. So you can move them as close, but 3 units should be the minimum spacing required. So we'll anyways keep it more than 3. I'm just placing them close enough so that they resemble to an inverter. Like the drain and the contact shouldn't be far away from each other. Now our transistor, P transistor is ready and N transistor, PMOS and NMOS is ready. Okay, so we'll need something to connect VDD and ground. Now I said we'll be using wells to avoid latch up. So PMOS will use N well. So we'll click on N well and click here. Then P well will be required by NMOS. Okay. Now you click on it and change the size to say 25, the X size, just large enough so that the entire transistor is covered. Okay, But now when you place wells, make sure that these two regions are in touch with each other, otherwise you might get an error. Okay, now with this done, let us make the connections. First click on the polysilicon and click on the other one. The connection is made. Now you can see a straight line coming since the entire inverter is aligned. Now suppose the inverter wasn't aligned, it was something like this, and you just made the connection. You can see a crooked line forming. If this inverter was given for fabrication, you don't know what might have happened here. You might just get a blot because such a small angle is not fabricated, right? So make sure that the design looks neat and tidy and everything is at 90 degrees. Okay, so we have connected polysilicon. Now I call this as my VDD and I'll call this as my ground. So I need to connect the source to VDD. So I left click and right click. I get a blue wire. This blue thing is metal 1. Contact to contact or contact to well, if you make a connection, you will get a metal 1. Now I've connected the sources. I'll connect the drains. Left click and right click. Now drains are connected. Now I'll just take one extension so that if I want to use my inverter further on, I have to supply input to this particular node. Similar is the case with output. Just left click and right click. Okay. Now the inverter seems ready, but there are a few things missing. We specified spice models. We need to specify spice models here too. So let's click on the PMOS. Make sure that you are clicking on PMOS and not on the active region. So when you click on PMOS, then go to Tools, Simulation Spice, Set Spice Model. Even here, just click on the NMOS, Tools, Simulation Spice, Set Spice Model. Now you can see it's too small, barely visible. So you can just use this toggle zoom magnifying glass, just drag, and yes, you see. So now to come out of this magnifying glass, we just click on the arrow. Now as you can see, I'm trying to select the spice model to change the name to PMOS, but that is not happening. Instead I have some node properties open. I don't want that. So what should I do? I'll press Ctrl and then click. My transistor is selected. Now again Ctrl and click. Now you see a red mark is formed. Yes, now this red mark forms means the spice model is selected. Now I open properties. Ctrl I and write PMOS capitals and say OK. But if you want, you can increase the text size, say by 3. So that's it's visible. And just scroll down. Similarly with the other one, I'll say NMOS and text size I'll keep as 3. Now I want to come back to my normal window. What do? I go to Window and I say Fill Window. Fill Window is an option which will fit the entire design to the window that is available. That is the workspace that is available. Now with this, we have named our transistors. But as you know, in schematic, VDD and ground symbols were available. So we directly use the available VDD and ground symbols. But now they are not available. So we'll have to name them. So we'll have to export. So we click on this well and say Ctrl E. Or you can just go to export and create export and name it as VDD. Make sure it is small letter VDD, and similarly Ctrl E and GND for ground. Don't write the entire thing GROUND, just GND is enough. Okay. Now what do we need? I'll use this contact. This, as you can see down here, is a metal 1 polysilicon 1 contact. So if I had to use my inverter in some other design, I wanted all the contacts, that is the connections, at the same level, and polysilicon is at a lower level and metal 1 is at the higher level. So I will use this contact to bring both of them at the same level. I'll just place it here and then left click and right click. If this doesn't happen, if you get something like a larger part like this, then just say Ctrl Z, align it well, and then left click, right click. It will happen. Fine. Now we need to name our export. So we'll say Ctrl E in for input and Ctrl E out. Now when you've selected and you are saying out and in, make sure that you are not clicking on the arc. Now when I click here, you can see this entire thing getting red boundary, but the entire arc is selected. But what I want, only the node being selected. When you click on the node, if you are not able to click, just press Ctrl and click. You can see some electrical connectivity, right? Make sure that you label the node and not the arc, and then say OUT. Okay, with this our inverter seems ready, but let us perform some checks. Then we'll go to Tools, DRC, and we'll say check hierarchically. What will this do? It will check for all the DRC rules, all the spacing rules, minimum width height rules. All those rules are checked by this check. So DRC stand for Design Rules Check. Just click. Oh, we found one error. Let's see how to solve it. Yeah, while making a layout and while checking the layout, make sure that your electric message window is open, because all your errors will appear here in the window. Now you can see type less than or greater than to step through errors. So don't click here, just click on the cell and type shift less than. Now you can see one of this region is highlighted and says minimum width height error. So now minimum width height would mean the X and Y should be in some proportion according to the design rules. So I just change the Y size to 6 and say OK. Now I go to Tools, DRC, check. You can see here, right? 0 error, 0 warning. So the design is perfect. Okay. Now before moving forward, I'll just show you a few more errors which can occur. Suppose I have this placed too close. Something like this. As you can see, while I was moving, the spacing it is showing with respect to this and not with respect to the poly. But the spacing is less than 3, so it will definitely give an error. Let's see. It gave an error. It gave 3 errors in fact. So I'll just say OK. No need to click anywhere. You don't need to click down here. Just make sure that you are in your workspace and then shift less than. What does it say? See, these two regions are highlighted first. The contact is highlighted and this polysilicon is highlighted. It says arc polysilicon is less by 1 than 3. It does not follow the Moses's rule. Now what does this rule? Less than 3. Basically, the distance between two poly is less than 3. Now why does it show such an error? You will say this is the same signal. How does it matter if the signal is even got together? Like if the space between this is no more during fabrication, and it is just one big spot here. It doesn't matter, right? But how electric sees it as, this is one wire, this is another wire, this is a contact, and between any two contacts, the minimum distance between any two contacts or contact and a wire or poly and contact, the distance should be 3. So we'll just take our contact away. Okay, now let's look for another error. If I had this metal one too close, it should give an error. Again, this is less. This doesn't give an error. The reason for the same is, you can see here, this is a complete green signal, whereas there is a contact. This entire thing is one metal one over it. Correct? We've connected the drains through metal 1. So let metal 1 be anywhere, it doesn't really matter. But if I had something like this and it was close enough, then this would be an error. See? Too close, right? Okay. Let me show you some other errors. Suppose you have this well too close. Can you see something known as error written there? Here above you will get to see N active to P active spacing is 7, 6.5, 6, 5, 4.5, and suddenly it is error now. The spacing, minimum spacing is 3.5, where spacing is 3.5 and minimum is 4. So according to design rule, the distance between the contact, the active region, and the well should be 4. So if I have this here and I do my DRC check, it is giving an error. In fact, it is giving multiple errors because it is saying not only one but the other contact and the transistor, everything is too close to each other. But if you have something this far, still it will give an error, because then it doesn't understand. It knows that there is some VDD which is to avoid latch up, but how will the well avoid latch up if it is not close enough? So these are some rules that you should keep in mind. And don't make your design like this. It doesn't make sense, right? Your drain is somewhere here and your contact is at a distance. Your contact should be right above your drain, correct? So making a design like this gives you errors. It says that they are not connected, and even if they were connected, like so close to each other, and then DRC, you still have errors. It says it is close by, but then it is not close enough. So we'll just undo everything. Yes, our Control Z, Control X, everything works here. So our inverter is ready. Now we have to complete the DRC check. After doing the DRC check, there is something known as ERC, that is check wells. This check wells is to check whether you have made provisions to avoid latch up, that is if the well regions are present and they are named VDD and ground. So we'll go to tools, ERC, check wells. No well errors found. Now comes one of the most important parts. Go to tools and NCC. In NCC, schematic and layout cells. Now NCC stands for network consistency check. This will check the layout with the schematic, and we just click and you can see NCC command completed. When you get NCC command completed, that means you've had no errors. But now suppose, what do NCC error mean? Now that means if you have any exports in your design and those exports are not matching with your schematic, then you get an NCC error. Otherwise, you'd get an NCC error if you have some complex design and suppose there is an input to one NAND gate A and the output of the NAND gate is going to an XOR gate, but in the layout you messed up with the stick diagram somehow and the input A is not going to the NAND gate, instead it is going directly to the XOR gate. So NCC will say that there is some error. Now let's see how the error looks like. What I'll do, I'll just delete the outs. So there has to be one export error. So I go to Tools, NCC and Schematic and Layout Views in Cell. Yes, you see here, you have one export error. See, you have two paths. In the schematic and layout, you have two paths present, 4 wires present, 4 ports in the schematic and 3 ports in the layout, which means one export is missing. And they've also written the export is out and you have just net 0. You need to name it as out. Now, not just not naming an export or not putting an export will create an error, but a spelling mistake or mistake in capital and small letters will also put an error. Suppose if I just say Control E and write capital O and UT, right? It's correct, isn't it? And I save it and I do NCC. See, now it says that there are 2 ports, 4 wires, 4 ports, but there is still an export error. When I click on it, it says in schematic it is out and in layout it is capital OUT. So make sure that whatever you export it well. Okay. So now since we are done with this, we need to simulate this. So the steps for making inverter layout are: first take the PMOS, NMOS, then we take the active regions, place them together and connect them, then connect the entire NMOS PMOS with the wells and get extensions for input and output. After that is done, we go to Tools, Perform, DRC, check hierarchically. After DRC, we perform ERC, check wells, then NCC, schematic and layout views in current window. Okay. Now we have to simulate, but there is no option to simulate as such. So what we'll do, we'll go to inverter schematic. We'll click on the spice code that is written, copy it, go to inverter layout and paste. If it's too small to be seen, then you can increase the text size to say 2. Fine. And run. So Tools, Simulation Spice, write spice deck. Okay, so we simulate. So we go to Tools, Simulation, Spice, write spice deck. We just right click and then we say add trace and then say V in and V out. Just click on the 2. Yes, in the previous slide, in the previous time when we made our schematic simulate, I clicked here, pick visible traces and I selected V in and V out. That is also one method and this is another method to just add trace. You can see V in and V out, right? Now, if you want to see your rise and fall times, press Ctrl L. See, you'll see the rise and fall times have changed, right? They aren't exactly the same as they were in the inverter. Now, this is because of the parasitics present. So, we are done with inverter. If you get something such, we don't need to really consider the waveforms, so just close. Now another thing that you can do is Suppose you want to use this layout in some other layout. So what do? Right, like you made this inverter sim schematic. You make another layout and name it again as inv underscore sim. Okay, so we have two, and I will have to delete this code, spice code, and in my inverter simulation I'll just click and drag just like we did for our icon. Now you can see here you have VDD out, in, ground present, right? If this was a part of another layout, I want to make a AND gate with the help of NAND gate and inverter. So I'll make one inverter separately and an AND gate separately and then combine the two, right? So this is how I combine it. Now if I want to see what is inside this box, I just click on the box and here the open eye symbol, I have to open it. Click on it so I can see what is inside. If I don't want to see, the close eye symbol. Okay. Now if I want to run this, I can't just put my code and say simulate because this knows nothing. These inputs that you see, VDD, in, ground, these belong to the inverter layout. But in this particular layout cell, there is nothing as such. So we just click on inverter and right click, ground, in and out. And we just name these as VDD, in, out and ground, like we did for the icon view. We took arcs and we named the arcs, so here also we are naming, and then we'll simulate. Tool, simulation spice, right spice check, add trace, v in, v out, and say okay. You get the same graph. The values are also the same. There might be a slight change here and there because of these wire and the parasitics present, but yes, this is also a way to simulate the inverter. So you have your inverter schematic and inverter layout ready. Save it. Thank you.